Good evening. Today we are going into the second part of our third chapter, motion in a straight line. In the previous session, we were discussing about the position time graph, the xt graph. Now, what we discussed in the last class was, suppose a body is moving in uniform motion, that is constant velocity, then you have the position time graph. Here we plot the position or the distance or displacement of the particle in time interval t, and you have a straight line because I told you that the slope of the line would mean the angle theta that the line makes with the positive x-axis. Slope of the line will be, slope is equal to tan theta, and this tan theta will give you the velocity. Tan theta, as you know, is opposite side by adjacent side. So if you have the opposite side here representing the position and the adjacent side here representing the time, we know that tan theta, that is the slope of this line, will give you the velocity. Now this represents a constant velocity simply because wherever you may draw the line, the angle theta, the theta is the same. So at every point the velocity remains the same, and therefore this line, when it is a straight line, it represents a body moving with a constant velocity, constant slope of the line. Now one more thing I need to tell you is, see, this angle that this line makes with the x-axis is an acute angle, and when theta is an acute angle, tan theta value is positive, and therefore this represents a body moving with positive velocity. Positive velocity, I told you, by convention, if you have the axis like this, and if this is the origin, to the right and towards the above the origin will be taken as positive. So this is a positive x-axis, this is a positive y-axis. To the left and downwards will be taken as negative. So when I say positive velocity, it means from the origin a body is moving, let's say, to the right or upwards. So the displacement of the particle is positive, and therefore displacement by time is velocity. The velocity is also positive. Now suppose we have, let's say, a body. So from the origin, the position of the body is going on increasing. So from the origin it has moved towards the right. Now suppose we have a body which is moving from the right back to the origin. It means it is moving towards the left. So its position x will come back to origin as time interval increases. That means since it's moving to the left, it has negative velocity. So then our line is going to be like this. Now here, the angle made by the line with the positive x-axis is an obtuse angle. So whenever we have tan theta with theta as an obtuse angle, the values are negative, and therefore we know that tan theta, which gives you the slope of the line, represents negative velocity. So this is a body which has a constant velocity, but the velocity is negative. That means it is moving to the left or moving towards the origin. If you see that, you will see here as time increases, the position of the body is coming back to 0. Okay, so this is a body moving with constant velocity, positive velocity, but this is a body moving with constant velocity, but it is a negative velocity. Same way, if I show you something like this, xt graph with no change in its position. Let's say from the origin, this is 5 meters. The body continues to remain at that position even though time is going on increasing. So this represents a body at rest. You will see that the slope of the line is 0 because this line is parallel to the time axis. There is, the theta is 0. So tan theta is also 0. So no slope. So that means this represents a body which is at rest. So I hope the three graphs are clear to you. Now the next thing that we need to go on to discuss is acceleration. You have average acceleration and also instantaneous acceleration. So suppose a body is in non-uniform motion. That means its acceleration is not zero, it has some acceleration. So your body is accelerating. So maybe its velocity is increasing or its velocity may be decreasing. There is a change in velocity. So you define average acceleration as a bar. Average acceleration written as a bar should be equal to, let's say at time t1, the body had a velocity v1. After some time at a new time t2, the body's velocity has changed to v2. So a bar, average acceleration, is final velocity minus initial velocity divided by t2 minus t1, which is what we call as change in velocity by change in time. And this is what we call as the average acceleration, whose SI unit is going to be meter per second square, because delta V, velocity, is already in meter per second. There's another time in the denominator, so it will be meter per second square. Now this average acceleration, so if let's say your body is in, I'm going to plot the xt graph for non-uniform motion. You will see that the slope of the length, in such a case, this body is in non-uniform motion, and in the previous section I told you, if you want to find the instantaneous velocity at a particular time interval t, you just draw the tangent and the slope of the tangent will give you the velocity at that time. Okay, so this body continuously keeps on changing its velocity, and therefore if you're going to talk about instantaneous acceleration, so at an instant, at that particular instant, or when the time interval delta t tends to 0, what is the acceleration? And that is what you call as instantaneous acceleration, written simply by A, which is limit of time interval delta t tending to 0, delta v by delta t is equal to dv by dt. So I have printed out the definition for that in your notes that I have sent you. The limiting value of average acceleration as a time interval delta t tending to 0 or approaches 0 gives the acceleration at any instant t, and written as dv by dt. Okay. Now to represent a body which is having an acceleration, it is changing its velocity, we have the position time graph. What we just drew before, this straight line graph that we drew was for a body moving with uniform motion, that is no acceleration. It has constant velocity. So then I showed you that if it has positive slope, then it has a positive velocity but constant. It can have a negative velocity, again constant velocity, or we also discussed the graph where a body is at rest. We are now going to discuss the xt graphs for bodies that move with acceleration. So if there is acceleration, the equation which you know, s is equal to ut plus half at square. Here I told you, since we are talking about, in your textbook this year they have used displacement as x. So I'm going to write x here. X is equal to ut plus half at square. So whenever you draw the xt graph, we know along the y-axis we are taking the x variable, the position, and here we have the time. So the x-axis has the time, and along the y-axis we plot the position of the body. So if you look at this x is the variable along the y-axis, equal to your initial velocity of the body. Initially, initial velocity is a constant. So I'm going to write that as a constant. T is a variable along the x-axis. So ax plus this half into a is another constant, because I told you the body is moving with constant acceleration. So if a is constant and half is also a constant, the whole thing I'm going to represent as another constant b, and t square. T is the variable along the x-axis, so I may write it as x squared. So here x is a variable along the y-axis. U, which is an initial velocity, which is a constant, I have represented with the letter a. T is a variable along the x-axis, so ax plus this whole thing another constant b, x squared. This represents the equation of a parabola. You will be learning, those who have taken up maths will be learning about parabolic equations, I think towards the end of this year or in the next year. But anyway, Even if you don't know this right now, please, I hope you've understood that this equation that we have here is of this form, and this equation represents a parabola. Now let us discuss the different, so when you draw the xt graph of a body moving with constant acceleration, since this is the form of that equation, we expect not straight line graphs. Straight line graphs, you would have got your equation in the form y equal to mx plus c that we discussed in the previous session. Now you see, when there is constant acceleration, the equation of motion is taking this form, which means the graph will be a parabola. Let us discuss the different cases here. Now let us look at this first graph, which I am going to draw like this. Here we have x, we have t here, and my first graph is here. Now this is the xt graph. In the previous session I told you the instantaneous velocity will be given by the slope of the tangent drawn at that instant to this graph. So suppose I have this instant as, let's say, t1, and I want to find the slope. Then I simply draw the tangent at that point. Then this is theta. Okay. After some time, let's say this is time t2, and if I want to find the slope, then the tangent will be drawn here, and that will be the theta. If I extend it down here, that will be the new theta. However, you will notice that at every point, theta is acute. I already told you, if theta is acute, then tan theta, the slope of the line, tan theta will be positive, which means this represents a body moving with positive velocity. So velocity is positive. Okay. Now as we move from t1 to t2, as time increases, you will see that the slope of the line is going on increasing. Can you see that this is the slope of the line at t1. By the time you reach t2, it has increased. The slope of the line goes on increasing, and therefore we know that the velocity is increasing. Now imagine a body is moving to the right and its velocity is also increasing. So a body is moving to the right, so it's got positive velocity. Its velocity is also increasing. If its velocity is increasing, it means that the acceleration is also in the same direction. Because what is acceleration? You already know F equal to ma. So acceleration will be in the same direction as force. So if a body is increasing its velocity, it means that a force is applied in the same direction. That means its acceleration is also in the same direction. Only then the velocity can increase. Therefore, we may say the acceleration in this case is also positive. So we have velocity positive, acceleration is also positive, its velocity is increasing, and such a motion we call as accelerated motion. Clear? So we have theta acute, and therefore we know that the velocity is positive. And since the steepness of the graph, here the steepness of this tangent was like this. As you move, the steepness is going on increasing. So the slope of the graph is increasing, which means velocity is increasing. So if a body is moving to the right, because I said that because velocity is positive and its velocity is increasing, it means that the acceleration also must be positive, having the same sign, and therefore we call it as accelerated motion. Now the next one that I am going to discuss is in the xt graph. The next graph I am going to show you is going to be like this. A graph, a parabolic curve like this. Okay, a parabola like this. Now here you will see I am going to take a tangent here and let's say a tangent here. So if I draw the tangent here, we see that this is the tangent, okay, and this is the angle that it makes with the positive x-axis. Similarly, a tangent here will be drawn like this. This is also theta is acute. So in both cases, so this is, let's say, at time t1 and this is time T2. So in both cases, you see that theta is acute, which means tan theta, which is for an acute angle positive. Slope gives you the velocity. So we know the velocity is positive. So the body is moving, let's say, to the right. Now, as you move from T1 to T2, this was the slope of the line at T1. As you move to T2, you see that the slope is decreasing. This is steeper than this. So as you move from T1 to T2, the slope is going on decreasing. That means your velocity is decreasing. Now, if your body is moving to the right, but its velocity is going on decreasing, that means obviously there is some force acting in the opposite direction. Your acceleration is therefore F equal to ma. Acceleration is opposite to velocity. So if velocity is positive, it means that in this case, the acceleration is negative. So I hope you understood what I said. At T1, this is the slope of your line. As you move to T2, the slope of the line is going on decreasing. And since the slope of the line decreases, we know slope being velocity, velocity is decreasing. So if your body is having a positive velocity, that means it is moving to right, but its velocity is decreasing. It means that the force is an opposing force, that is acceleration is in the opposite direction. So I have taken acceleration as negative, and since its velocity is decreasing, we call it as a decelerated motion or a retarded motion. So we may call it as decelerated motion or retarded motion. We next have another graph where we have the shape of the graph like this. We have the shape of the graph like this. I'm going to draw a graph, again another curve, a parabola. So this is the first time interval T1, and let's take this as the next time interval T2. So at this point, if I draw the tangent, the angle that the tangent makes with the x-axis, you will now see is obtuse. Here if I take T2, you will see this is the tangent drawn. That also makes an angle theta which is obtuse. If theta is an obtuse angle, I told you that this tan theta of obtuse angles will be negative, and therefore the velocity is negative. So let's say the body is moving to the left. It's got negative velocity. Okay. It's got a negative velocity. Now, as you move from T1 to T2, T1 was like this. This was T1, this was the slope. As you move to T2, this is becoming more and more steeper. I hope you're noticing that. This is the slope of the line at T1, this one. As you move to T2, this is the slope of the line. So you see that the slope of the line goes on increasing. And if the slope of the line increases, slope giving velocity, we know the velocity is increasing. So now if velocity is towards the left and its velocity is increasing, that means there is a force in the same direction. That is, acceleration is also in the same direction. So since velocity is negative, here acceleration is also in the same direction. It is negative. Now since velocity is increasing, we call this motion as accelerated motion. Accelerated motion, because your velocity is going on increasing. Okay, now the last one, the shape of the graph we are going to discuss, the last curve, what we are going to discuss is this. Let's say we have a curve like this. Okay. So at two time intervals, let's take this as T1 and this as T2. If I draw the tangent here, this is going to be the tangent, and at this point, this is going to be the tangent at this point here. So you see again the angle is an obtuse angle. Obtuse angle would mean tan theta is negative, so its velocity is negative. So that means it's moving to the left, negative velocity. But you see at T1, this is the slope of your line. By the time you come to T2, your slope of the line is decreasing. So here we have T1, and as you come to T2, the slope of the line is decreasing, and therefore we know that this velocity is decreasing. And I told you, if your velocity is decreasing, That means there is some opposing force. That means the acceleration is in the opposite direction. Your acceleration is in the opposite direction. So V, when it is negative, acceleration then must be in the positive direction. Since velocity is decreasing, we call this as decelerated motion, or we call it as the retarded motion. Okay. Now in your textbook, so you would have noticed from the four graphs that we just discussed now, you would have noticed one thing, that is when both velocity and acceleration have the same sign, that is if both A and B, both of them have same sign, suppose both of them are positive or both of them are negative, then it will be accelerated motion with its velocity increasing. But if both A and B have opposite signs, opposite sign, that is one is positive, the other is negative, then it will be decelerated or a retarded motion. Or a retarded motion. Okay. Also, what you have in your textbook is they've combined all the four together, they've combined and given it to you as two graphs. That is the xt graph here. In the four graphs that we discussed just now, this graph and this graph, that is from here I have shown you that this and this graph, both of them represent positive acceleration. So in your graph, they've combined this and this together to give you a positive. So this represents a body moving with positive acceleration. Okay. Similarly, the next one, if you have xt graph like this, in your textbook they've shown you like this, where in the four graphs that I just discussed, you will notice that this one and this one represents the motion of a body with negative acceleration. So this together, this represents a body moving with the xt graph of a body moving with negative acceleration. Okay. Now the easy thing to remember that I always tell students is this is a smiley face. So smiley face will, the xt graph with a smiley face is representing a positive acceleration. This with a sad face represents a negative acceleration. Okay. So these are the graphs that I needed to discuss with you. The xt graphs for a body moving with positive acceleration and also a body moving with negative acceleration. Now we can move on to the VT graphs, that is the velocity time graph. So the velocity time graph called as the VT graph. So if you are going to draw the VT graph of a body moving with uniform acceleration or constant acceleration, the equation that connects the velocity and acceleration is V equal to U plus AT, or I may rewrite it as V equal to AT plus U, right? So if we have a graph where we are now going to plot the VT graph, you see that the variable along the y-axis is the velocity, the variable along the x-axis is time. So here, the variable along y-axis v, so this is y equal to, acceleration I told you is a constant acceleration. So this will be, let me call it as m. T is a variable along the x-axis. So x plus initial velocity of a body, starting velocity is a constant, and that I will represent as c. Now if you see this equation, you must know it is a straight line graph, y equal to mx plus c, whose slope is given by m, which means the slope of the VT graph, a straight line graph, will give you the acceleration. So suppose I draw a straight line graph like this. Again I am telling you the slope of the graph will be tan theta. So tan theta or the slope of this line will give you the acceleration of the body. Had it been xt graph, the slope of the line will give you velocity. Vt graph, slope of the line will give you the acceleration. Now that's simple to note. See, suppose a body had, let's say, velocity v1 at time t1. After some time, its velocity is v2 at time t2. Now, slope of the line I told you is the tan theta. So, if I take, let's say, this is theta. Theta all everywhere will be the same. This is v2 and this is v1. So, opposite side is, this is v2 minus v1. And the adjacent side here will be t2 minus t1. This one, t2 minus t1. So, if I take tan theta, we have this as v2 minus v1 by t2 minus t1, which is delta v by delta t, which will give you the average acceleration in that time interval. Now, because this has constant acceleration, at every point you will see theta is the same and tan theta will, the slope of the line will be the same. That means this represents a body moving with constant acceleration. Then the same way you can, so here again we have three graphs to discuss. We can have a graph like this where VT graph. If I have a straight line like this, it means that there is no acceleration, because let's say this is 5 meters per second. You will see that the body is moving with a constant velocity. The slope of the line is 0, which means the acceleration is 0. It doesn't have any acceleration, uniform velocity. Then this line, this one, VT graph. Let's say this is your slope of the line is a constant everywhere. So you will see that this is an acute angle, and tan theta for acute angles will be positive. So this represents a body moving with positive acceleration. VT graph of a body moving with positive acceleration. Similarly, you have a VT graph for a body moving with negative acceleration like this, because you will see that the angle that the line makes with the positive x-axis, theta, is obtuse. If tan theta or theta is obtuse, then it represents a negative slope. Negative slope means negative acceleration for a VT graph. So this is the VT graph of a body moving with negative acceleration. Then in your textbook we have 4 different graphs, VT graphs given to you. The first graph is something that we already discussed, T, and this is V. This is the line given to you, graph. This VT graph, constant slope, would mean that it has constant acceleration, acceleration. And because theta is negative, acute, it shows that it is a body moving with positive acceleration. And because the graph is in the positive quadrant, this is 0, this represents positive velocity and this represents negative velocity. So this is graph of a body moving with positive velocity and positive acceleration. Acceleration is given by tan theta. Theta is acute. So you know that the slope of the line is positive. So slope of the line giving you acceleration, acceleration is positive, and because it is in this quadrant, velocity is positive. Okay. So positive velocity and positive acceleration. Then the second graph that is given to you in your textbook is this one. We have what we discussed just now, VT graph, right? Because theta, that the line makes with the x-axis is obtuse angle. I told you tan theta of an obtuse angle will be negative, and the slope of a VT graph gives you acceleration. So we know that the acceleration is negative in this case. But your body, I told you this is origin. So here velocity is positive, here velocity is negative. So this is a body moving with velocity which is positive velocity, which means it is traveling in the positive direction. Then the next graph that is given to you in your textbook is like this. Again, the VT graph, but it's been given to you like this. Okay. Now here, angle made by the line with a positive x-axis, theta is obtuse. If theta is obtuse, then tan theta is negative. Since it's a VT graph, the slope gives the acceleration. So we know in this graph also acceleration is negative. But your body is, you see the graph is in the negative axis. This is the velocity axis. Here it is a positive axis. Here it is the negative axis from the origin below. That is, velocity is negative. It's moving in the negative direction. Velocity is negative. Acceleration is also negative. And the last graph that you've got there in your textbook is shown like this. It is the VT graph, and this is time t1, right? Now here you will see, so this is the origin. So from 0 to time t1, the body has a positive velocity, because you see this is in the positive quadrant. The body is moving in the positive direction. And then what happens is, at time t1, the velocity becomes negative. So it is changing direction, and here velocity becomes negative. In the second quadrant, here in this quadrant, the velocity becomes negative. So at time t1, from 0 to t1, the body is traveling in the positive direction, and after t1, the body is traveling in the negative direction. But you will see throughout, it's got a negative slope, because the angle that the line makes with the positive x-axis throughout remains the same. So the slope of the line is negative and constant. So that means slope which represents the acceleration is constant and negative, because the slope of the line is not changing and it is negative. Okay. So this represents the motion of a body which from 0 to t1 travels in the positive direction with negative acceleration constant. And at time t1, it changes its direction. It goes into the opposite direction, but continuing with the same acceleration, which is negative and constant. I will give you a simple example of this. Suppose a body is, let's say, we have a body being thrown up, okay, and then it's coming down. Now let's say this is the initial velocity. By the time, if you throw a body up, at the maximum height its velocity will reduce to 0. So here the velocity will reduce to 0, and let's say it reached here at time t1. So its velocity now is in the upward direction. Upward direction means velocity is positive. But a body that is being thrown up is acted upon by acceleration due to gravity, which you already know. Acceleration due to gravity is always towards the center of the earth, that is downward. So that is always minus 9.8 meter per second square. I hope you have already learned that in 9th standard. Acceleration due to gravity has a constant value, always 9.8 meter per second square, and it is always directed downwards. So it's negative. So you see that this portion of the graph shows you a body that started with some velocity, let's say initial velocity u, and as it moves up, its velocity reduces to 0. Its acceleration is negative and a constant. At time t1, its velocity has touched 0. Then after that, it's moving down now. So its velocity is negative. Acceleration is still g, which is, this is g. Acceleration is still g, which is minus 9.8 meter per second square. So you see this part of the line, the velocity has become negative, acceleration remains the same at minus 9.8 meter per second square. So this represents a body which is thrown up and then returns back. In this portion, we see velocity being upward is positive, but acceleration is negative and constant. At time t1, it reverses its direction, it's coming down, so its velocity goes into the negative axis, but its slope, which gives you the acceleration, remains at minus 9.8 meter per second square. The next thing that we need to discuss under the VT graph is, the first thing that I told you is, the slope of the VT graph gives you the acceleration. Next thing I am going to show you is, see, let's take a simple case where we have time here and velocity here. Okay. I told you, if I draw a straight line, it represents a body traveling with uniform velocity, no change in velocity. Okay, let me take the area under the graph. This is the area under the line. This is a graph, area under the graph. So, area under the graph, area of rectangle, let's call it OBDA. Okay, OBDA, rectangle, OBDA. We know area of a rectangle is length into breadth. The length is OA into the breadth is OB. Here it represents the time. So we know this is going to represent the time t multiplied by here we have the velocity. So let's say it's moving with uniform velocity. Let's say its velocity initial is u. It continues with the same velocity. So throughout it has the same velocity. So that means this represents, what is this? From 0 to u, and this is the time t. So OB is into u will give you the area of graph, which is ut. Okay. Now we know this formula, S is equal to ut plus half at square. Now since this body is moving with uniform velocity, we know it's not changing, constant velocity. So its acceleration is 0. So if acceleration is 0, then this whole term becomes 0. So the displacement of the particle is simply ut for such a graph. If you compare these two equations, you will see that the right hand side of both the equations, let's say this is equation 1 and this is equation 2, the right hand side of both the equations is the same. So naturally the left hand side also should be the same. So we see that the area under the VT graph gives you the displacement of the particle in that time interval t. Okay, I repeat. From this we see that the area under the VT graph will represent the displacement of the particle in that time interval. Okay. So two things you know from the VT graph. The slope of the line. Look at the slope of the line. Here the slope of the line is 0. Slope of the line gives you acceleration, VT graph. So this body moves with 0 acceleration. The second thing that we learned from the VT graph is area under the graph will give you the displacement of the particle in that time interval. Okay. Knowing these two things, we can now derive the three equations of motion, which I think you already did in 9th standard, but we have a repeat of that in class 11. So, equations of motion, the three equations of motion we are now going to derive using the VT graph. So, we have a diagram here. I will draw it just like you have in the textbook, so that when you learn, you don't have a confusion. The VT graph. Here we have the t, time. Here we have the velocity. We are representing the velocity. And here we represent the time. So we will draw the straight line like this. What does this mean? At time t equal to 0, the velocity, initial velocity is not 0. This represents velocity, right? So if I have a graph which starts like this, velocity here and time here, it means that at time t equal to 0, the velocity of the body is also 0. But for a graph like this which starts at a point here, at time t equal to 0, the velocity is not 0. Let's say it is 5 meter per second. So its initial velocity is not 0. It has some initial velocity which I am going to call as u. Initial velocity I am going to represent as u. So at time t equal to 0, its initial velocity is u, and this is 0 time, and at some time t, it has reached, let's say this is time t, it has reached a new velocity, and the final velocity I am going to call as v. So this line represents a body whose initial velocity at time t equal to 0 was u, and at time t, some other time t, its velocity has increased to v. So that means it has an acceleration, and since it is a straight line, we know that the slope of the line gives you acceleration, and we know that it has a constant acceleration. Okay. So now I am going to call this as point as A, this point as B, this point as D, and this point as E. Right? Now this is going to be what? From here till here we have B, and from here till here we have U. So this must be B minus U. Right? Because from here till here it is B, and from here till here it is U. So this will be B minus U. And how much will this be? From here to here it is U. This is how much? From 0 to t, that is t. Okay. Now, first equation, to derive the first equation of motion, we simply take we know already that the slope of the line will give you the acceleration in a vt graph. So if I take this as theta, then I know slope of the line, that is tan theta, should be opposite side by adjacent side. For this triangle, opposite side is b minus u. So that is b minus u by, this is what? From here to here it is time interval t. So t, and this slope gives you the acceleration. So that is v minus u by t, and we have our equation v minus u equal to at, or v is equal to u plus at. That is your first equation, v equal to u plus at. The next thing that we have is, we see that this is a trapezium, and I already discussed with you just now that the area of the graph gives you the displacement of the particle in the time interval t. So area under the graph, that is this whole area, we may find the area of trapezium. So area of trapezium, OABE, area of the trapezium, I hope you know it, half into this is your trapezium, and the parallel sides these are the parallel sides. So this will be the perpendicular distance between the parallel sides. So half into t into the sum of the parallel sides. This is u. So this is u plus, from here to here it is b. So u plus b. I hope all of you know that the area of the trapezium. So suppose you have a trapezium like this. This is your trapezium. These are the two parallel sides. This is A and this is B. And this is the height I am taking. Area will be half into h into A plus B. This is the formula for area of trapezium. So that is why I am written a half into, this h is this side here, t, into the two parallel sides. From here to here we have u, and from here to here we have that full b. Okay. So that is how we got this formula here. And I now going to substitute half into t into bracket u plus, we just derived the first equation b equal to u plus at. So instead of b I am going to write here u plus at. Okay. Now from here I can say this is going to be equal to half t bracket 2u plus at. The area of the trapezium gives you the displacement of the particle s. So this is equal to, if I open the brackets, this 2 and this 2 will get cancelled. Ut plus half t into at will be half at square, or s is equal to ut plus half at square, which is your second equation. So we got the first equation from the slope of the graph, b equal to u plus at. We got the second equation from taking the area of the trapezium, s is equal to ut plus half at square. We have one more equation, that is the third equation. For that also, you take the same thing. That is the area of the trapezium itself, which will give you the displacement of the particle, except in the previous one we substituted for b. Here I am going to substitute for t from our equation. A equal to b minus u by t was the first one that we wrote, slope of the line. Acceleration is opposite side by adjacent side. So from here, what is t? T is equal to b minus u by a. I am going to substitute that t here. So we have s is equal to half into v minus u by a brackets v plus u. Instead of u plus v, I wrote it as v plus u. Now you know the mathematical identity. A plus b into a minus b will be a square minus b square. So v minus u into v plus u will be v square minus u square. Therefore I can write s is equal to half into this will be v square minus u square by, there is an a here. If I take the 2a to the left hand side, I may write v square minus u square equal to 2as, which is my third equation. So third equation is v square minus u square equal to 2as. So we have derived all the three equations of motion, v equal to u plus at from the slope of the graph, then taking area of trapezium, substituting for v as u plus at, we got the second equation, s is equal to ut plus half at square. Then taking the same thing but substituting for t from our first equation, we got the third equation, v square minus u square equal to 2as. Okay, so that is the end of this chapter. I'll send you the problems and we'll discuss them online. Thank you.